So let's start. We will be finishing the last topic, last part in this lecture. So later on, we will be tackling the tutorial questions, tutorial 7, and then that will be all for the module. So let's have a quick recap on what we have gone through. Mainly, topic 7 is on second order ODEs, second order linear ODEs, right, to be specific. So you notice that actually for your examination, it's all ODEs. Basically just different kinds of ODEs and then apply the blue box, whichever blue box is appropriate. So in topic 4, you have your first order linear ODE. And then after that, you have your first order systems of ODEs. And then it extends to now second order, right? So there are actually just, for this module, there are two solution methods, right? Just two solution methods. One is the Duhamel's principle, and the other one is Laplace transform, right? So basically just solving ODEs in their different kinds and then using Duhamel's or Laplace transform, that's all. Okay, so of course along the way you get some derivation problems as well, and certainly you will need to relate the math to the physics. That's what the math is for. Okay, we are trying to interpret what is the implications, right, to the engineering through the physics. So we have gone through the Duhamel's principle already for the second order ODEs, right, linear ODEs, and it is always comprised of two parts: the homogeneous solution. So homogeneous solution, there is no need to rederive. So if the question, you see there's a second order, and then they ask you, if it's not, or rather if it's homogeneous, meaning to say there's no excitation term, right? Then really you just go and find the eigenvalues, and from the eigenvalues you decide which solution form you want to use, right? So if your eigenvalues are real and repeated, then your homogeneous solution is just this guy here. Okay, so then what you do is that if they give you the initial conditions, then you proceed on to find your C1 and C2. Okay, simple as that. So there's no need to rederive because derive already. So then certainly if you get the excitation term, you should be able to recognize, right? If you have an inhomogeneous ODE with an excitation term, then certainly after you solve for the homogeneous solution, you also have to solve for the particular integral. Okay, so you can see the particular integral is just this guy. So basically you just sub your f of tau inside and then perform some integration. Okay, so that's Duhamel's, but there is Laplace transform as well. So it depends on the question you get, right? So if the question asks you to just solve, never say you use which method, right? Then it's up to you lah. Okay, you prefer Duhamel's or you prefer the plus. Okay, it's up to you. Okay, but if the question did state or use Laplace transform, then of course you are constrained, okay, to use the said method. So now we look at Laplace transform, how it can assist us to solve second order ODEs as well, right? Both homogeneous and inhomogeneous, right? So it's similar to the first order ODEs, where we also have gone through two methods, okay, Duhamel's and Laplace. So just to have a quick recap on the Laplace transforms. So as you can see, this is our Laplace transform table, which we'll be using to solve the second order ODE. And we will certainly need the Laplace transform of the derivative. In this case, we will need G prime and G prime prime because we have second order ODE to solve. So this is the guy. So now we are going to solve the last problem, right? Which is an inhomogeneous excitation or excited system problem, right? Because you can see the f of t there. Okay, so we shall not rederive the ODE. We can just copy and paste from here, right? Okay. So then we'll just apply Laplace transform on this ODE with the initial conditions. Remember, that's the beautiful thing about Laplace transform. Okay, the initial conditions are straight away given here. So when you perform Laplace transform, right, you straight away apply them into the transform equation. Okay, so our IVP will be y naught equals to 0, so no initial displacement, then y prime naught is equivalent to 1. Okay, so there's an initial velocity of 1 meters per second for the mass here. So that means that if you do a Laplace transform of the entire ODE, then you're going to get, so you look at this guy here. So it's going to be s square. So y prime prime will be y of t after you take Laplace transform will be big Y of s. Okay, so the first one is s square big Y. I omit the of s, right? So less things to write. Then after that, you have your minus of s g naught, which is your y naught. So therefore, this will be minus s times 0. Then minus y prime naught, which is 1. So that will be for the first term. Maybe let me underline. So this guy, after you take Laplace transform, you'll get the blue part here. Okay, because you are using this second row. So then subsequently, you just proceed on to take the Laplace transform for the second term, which is plus 6. Then you see the y prime here. So y prime here certainly is going to give us s big Y, because you're looking at this first row. And then minus g naught. So minus y naught is 0. Okay, so this will be for y prime after you take Laplace transform. And then finally, your 9y, right, will be plus 9 big Y. So then you must remember to take the Laplace transform of 2e minus 3t. So therefore, that is going to give us 2 over s plus 3. Is that right? Okay, because e minus 3 is your so-called s shifting, right? So it's a minus 3, so it will become minus 3, so it's a plus. Okay, by now, hopefully you are somewhat familiar with Laplace transform already. So if that's fine, then the usual trick is to just isolate y, because that's solving the Laplace problem for your unknown function big Y of s. So then this guy will give us s squared plus 6s plus 9. So you do see the auxiliary equation, right, being manifested after you take Laplace transform. That's expected. So you got 2 over s plus 3. So then this is a plus 1, right? Okay. So the minus 1 you bring across become plus 1. So certainly this guy is going to give you s plus 3 square. Okay. So therefore you will have to divide throughout by s plus 3 square. So that is going to give you the big Y of s. So therefore your big Y of s, the solution in the Laplace space, is going to be 2 over s plus 3 cubed then plus 1 over s plus 3 square. So at this juncture, it begs the question, do you need to do partial fractions? The answer is no, right? Because this is already ready for inverse transform, if you didn't realize. Because this looks like 2 over s cubed. This looks like 1 over s square, but with an s shifting what? Agree, yeah? So therefore, if you take the inverse transform, you can just reverse the s shifting and you get your e to the t term. Okay? Can Any questions? Okay, if no, then you take the inverse transform. So Laplace inverse, because you are trying to solve for your y of t. Then inverse of big Y of s. So therefore, this is 2 over s cubed. Looks like 2 over s cubed, but with a shift. So 2 over s cubed, if you inverse transform, is going to be t square. So t square times the shift, e to the minus 3t. Okay? T square e to the minus 3t. Then the other one is 1 over s squared. So if you inverse transform, you're going to get t. Because the Laplace transform of t is 1 over s squared, but with a shift. So s shifting, e to the minus 3t. Okay, so that's what gives the solution here. So exactly, this is your solution and that's it. Any questions on the usage of Laplace transform in solving second order ODEs? Of course, this is an easy example. The reason is because there is no need for manipulation at the y of s function before you do your inverse transform. If you need to do manipulation here, then it might not be easy. It could be very tedious. So it's really up to what you get at this point. Any questions? Good. So I hope you are happy with this. So this Laplace transform. Yeah, and then this is another practice again on the Laplace transform also. So we solved this earlier as well using Duhamel's, or sorry, not using Duhamel's, using the general solutions. Okay, because this is a homogeneous system. This is homogeneous. Okay, equals to 0. But I mean, when you use Laplace transform, you don't really care whether it's homogeneous or inhomogeneous, right? Basically, you just Laplace transform the whole ODE, right? And then see what you get. So Laplace transform the whole ODE again, and you are going to get s square big Y minus, so your sy naught, no need to write, okay? Okay, I put minus 0 first. Then after that, minus of y prime naught, so that's 1. Then plus 10 multiplied by s big Y minus 0 again. Then plus 9 big Y, so equals to 0. Okay, so therefore this guy is going to give us y times s squared plus 10s plus 9. So you see auxiliary equation appearing again. Then in this case, right, you have a 1 here. Okay, you have a 1 here. Then subsequently, you're going to get factorized this to be s plus 1, s plus 9. Okay, that's how you can get a plus 10s. So therefore, this becomes y of s equals to 1 over s plus 1, s plus 9. Okay, so this calls for partial fractions. Okay, but since you have linear factors, so therefore it will be easy. Okay, so therefore this guy is going to give you something over s plus 1 plus something over s plus 9. So what you can do is that use cover up, right? So therefore covering up this s plus 1, and your s got to be minus 1, right? So 1 over 8 then. So then the other guy got to be minus 9, so it has to be minus 1 over 8. Okay, so once you have that, right, then you realize that you can actually do your inverse transform. So y of t equals to Laplace inverse big Y of s. So you can factorize out the 1 over 8. Then after that, 1 over s plus 1, you have e to the minus t. Then after this is a minus, right? Minus. So e to the minus 9t. And that's it. Okay, so you can see that if you use Laplace transform, you still need to do your partial fractions here. Okay, but if you were to use the general solution, then what you need to do is to realize that you get real and distinct eigenvalues. Okay, as you can see from here, minus 1 and minus 9. Then after that, you just sub into the e to the minus lambda 1t, e to the lambda 1t and e to the lambda 2t general solution. Then you have your C1 and C2, right? Then you need to apply the initial conditions to find C1 and C2. Okay, so that if you'll be to be using the general solutions. Okay, if you're using Laplace transform, then this is what you have. Yep. Yeah. Sorry, say it again. 1 over 8. Correct. So this is the particular solution already, because you don't see C1 and C2, right? So therefore, the Laplace transform method introduces the initial conditions right at the very beginning. So the initial conditions is already applied right from the beginning when you apply Laplace transform. So this is in contrast to if you were to be using the general solutions, and I refer to the general solutions here, right? So this is the one. So if you have real and distinct eigenvalues like what we have just now, right? Namely minus 1 and minus 8, then you are going to substitute into these general solutions, and you will see that you have a C1 and C2 to find. Then the C1 and C2 you can find by applying the initial conditions later on. Meaning to say, you get the general solution first, then you apply initial conditions. Okay, so this is not the same as when you apply Laplace transform, where you straight away apply the initial conditions when you take Laplace transform. It's totally different. It's two different methods. Okay, so basically, as I've mentioned earlier in the class, right, it's all about your finals is all about Laplace transform and Duhamel's. Okay, just these two things. Then basically just solving different kinds of ODE types. First order, system of first order, or second order. Just these three lah, right? So it's very focused. Okay, there isn't a lot to worry about. So now we are going to go back to our original objective, because right in the beginning of this topic, right, we are trying to analyze the vehicular suspension system. Okay, but just now, I mean, as in the beginning, we assume that the mass is connected to the spring and damper, then after that connected to the ground. Okay, so of course that is for ease of explanation and maybe to have a gradual introduction into the second order ODE system. But practically, you cannot expect the vehicular chassis, right, to be connected to the ground directly, because there's obviously a wheel in between the ground and the chassis. Okay, so you can see this is the more realistic representation, right, of the vehicular suspension. Okay, so you have a wheel that is connected to the hub assembly, then the hub, right, is connected to your suspension system, okay, which comprise of the spring and damper. So you can see the mathematical model will look something like that. Okay, so there's a wheel here, right? In reality, the even more practical model is such that, right, this wheel and the tire, you must understand that the tire is actually deformable. So what's going to happen is that if your tire made up of rubber, right, is deformable, then the tire actually behaves like a spring and damper. The tire itself is another spring and damper, and I mean, you can experience that, because if you were to deflate your tire such that it becomes very soft, right, then as you go through a hump, you probably cannot feel so much of the disturbance, because the tire is actually compressing, right, to absorb the shock. Okay, so therefore, if you want to have a even more realistic representation of the car suspension system, right, is a cascaded spring damper system. So there's a spring and damper here, then at the wheel, right, there's another spring and damper before it connects to the ground. Okay, so that will be a more realistic model, which I think I forgot if your tutorial question has one of that. Okay, but let's just look at this simplified but yet realistic vehicular suspension model here, okay, and try to solve it. So the whole purpose of the vehicular suspension system is to isolate the passengers from the disturbances on the road, right? Such that they have a more comfortable ride, okay? So you can see that the model here, right? If you draw the free body diagram of the mass or of the chassis of the car, then you notice that we're once again going to take reference from the equilibrium position. Okay, meaning to say the mass has been so-called allowed to be at a stationary equilibrium such that the spring here is compressed. Okay, so we're just going to take that as a reference. Therefore, you don't see any mg term here. Okay, there's no mg term, right? And then what's the deal with this k times y minus w? So you must understand that looking at the displacements here, first of all, you have the displacement of the chassis, and in this case, we consider upwards as positive. Okay, you can of course consider downwards as positive, no problem. Okay, just that this model considers that. So upwards positive for y of t, and then upwards positive for the w of t. So what's the deal with w of t? You must understand that the wheel is also in motion, what? Correct or not? The wheel can also jump up and down, right? Depending on the road disturbances applied to the wheel. So therefore, there's a wheel movement and there's a chassis movement. So what is the force by the spring on the mass? Okay, if you have y and w being non-zero, now you must understand that this is k times y minus w. So you have to think logically. Why is it y minus w? Why is it not just ky? Because if your y and w, the wheel and the chassis, move by the same amount, then practically you are not changing the compression length of the spring. What? I repeat that again. If let's say your y, your chassis move by 1 meter, the wheel also move by 1 meter. So that's as good as saying the whole thing move up by 1 meter. What? So there's no change in the length of the spring. So how can there be an additional spring force? No. So therefore, if you have y minus w, that correctly accounts, right, for that. Because if let's say this is 1 meter, then 1 meter minus 1 meter is 0. So there's no additional spring force here because it's a 0 spring force. Understand that? Okay. So how would you get a spring force here? It's only when y is not the same as w. Then you are relatively pulling or compressing on the spring. Okay, so you can imagine if y is more than w, that means this mass, right, moves up at a greater distance as compared to the wheel, then there is a stretching of the spring. So when the spring is stretched, the force must pull down on the mass. Okay, and vice versa, of course. If y is less than w, then obviously there's compression. So if y is less than w, then this guy will be negative, right? So if this is negative, then it will be pointing up instead. So therefore, everything makes logical sense. Yes, correct. Yep. Oh, how does it move up? Like in the first place, right? Yeah. So for example, if you look at the drawing here, right? If your car is moving along the road, then it hits a curb, for example. Okay, can hit anything like harm or curb or whatever, doesn't matter. So let's say it hit a curb. So what's going to happen is that initially the wheel is going to go up, right? So when the wheel go up, you notice that y is 0 initially because y is not moving yet. But the wheel is going to sense the disturbance first. Then it's going to go up. So w is going to have some positive value, but y maybe is still 0 initially when it hits the curb. So what's going to happen is that there is a 0 minus some value of the wheel displacement. You see that? Then it will be a negative term, right? Because it is negative times k. So this is a negative force. So when you have a negative force, what's going to happen is that this arrow is going to be pointing upwards because it's negative. So it pushes on the mass. But which is correct, what? If let's say the wheel hit the curb, it suddenly pushes up. So it's going to compress the spring. Then the spring compression is going to cause the mass to bounce up at later time. You understand that? K is a spring constant, is a constant. It's just the stiffness of your spring. Yeah, so K is a constant. Exactly. It is just a delayed response. Yes, later on, right, it will work out itself such that it will still be in equilibrium. Can So if you understand this logical sense of direction on the spring force, then you just apply the same understanding to the damper force. Okay? So the damper is also imposing a force on the mass, right? But this is because damping, right, is a force that is proportional to velocity. So when you remember the analogy I mentioned, right? You go to the swimming pool, you try to move your hand, okay, in the water. So if you move faster, you feel more force, right? Due to the resistance of the water on your hand. So therefore, the damper force is proportional to the velocity. So same thing. If you have the mass and the wheel moving at the same velocity, that means y prime and w prime is the same. So therefore, there is no damper force. Makes sense, right? So only when you have relative differences in the velocity of the mass to the wheel, then you can have a damper force. Because that means you are actually trying to push or pull on the damper. Can Okay? If both of them move at the same time, at the same speed, then the whole thing just move together. So therefore, there's no damping force. Okay? Because you're not pushing or pulling on the piston. So let me write an explanation here. So basically, the spring and damper forces arise due to relative motion. Due to relative motion between mass and wheel, or rather between car body. Okay, the keyword is relative. That means if both of them move together, then actually you're not doing anything to the suspension system because you don't get any force. Okay? Yeah, so after we have drawn and understood the FBD, then we can just apply Newton's second law, right? That's what we do best. So therefore, the forces are, so because we assume outwards positive, so downward will be negative. So you can see minus k times y minus w minus c times y prime minus w prime, the two forces here, equals to my prime prime. Okay? So, so notice that I also mentioned that because we take reference from the static equilibrium. So therefore, no mg term. No mg term. Okay, so this one we discussed it before already. So hence, if you isolate the ODE, you notice that you get a standard form on the left, my prime prime plus cy prime plus ky, right? This is the terms that we have been obtaining in the earlier slides. But there is a right-hand side. Okay, so the right-hand side is exactly the damping force due to the wheel movement, the wheel's velocity, as well as the spring force due to the wheel displacement. Okay, so you can see the two terms here by the wheel is like an excitation. And that makes total sense because it is the wheel movement that is going to excite the chassis, so much so that the chassis is going to be under disturbance. Okay, that means it's basically the disturbance from the road transmit to the wheel transmit to the chassis. Okay, so we are really trying to minimize or modulate the transmission of the disturbance from the wheel to the chassis. Okay, because if you do not have this suspension system, right, then you are assured that the disturbance is going to get transmitted to the passengers directly. Then you are going to have a very harsh and uncomfortable ride. Okay, so now we are going to expand how we define the wheel displacement and the wheel velocity dependent on the type of road disturbance that the wheel is encountering. So we are just going to imagine that there is a road disturbance of a step of height h, okay, encountered by the wheel at t equals to a, right? So as the vehicle is rolling along the road, then at t equals to a, suddenly mount curb. How many of you mount curb before? Serious? All never mount curb before? I mount curb a few times. Mount curb before, right? Straight away mount. So now the test is that you mount curb straight away fail, right? Yeah, yeah, yeah. Yes. So the same lah, the same standard now. Yours is what? Huh? Oh, I see, I see. I see, I see. Okay, okay, fair enough. Yeah, so cannot mount curb lah, right? Okay, let's say the vehicle here, right, mount curb. Okay, so mount curb, because curb is like a sudden step up, what? Right not? So let's say the curb is of height h, and you mount the curb at t equals to a. Then obviously your wheel displacement function can be modeled by a step function of height h, what? So it's just really step function u of t minus a, right? Multiplied by the height of the curb. Okay, so therefore that will be your wheel displacement function. Now, in order to get a wheel velocity function, very simple, you just differentiate the wheel displacement function. So therefore, if you were to differentiate the unit step, you are going to get the delta function. Okay, when you take the derivative of the unit step, it's actually the delta function. Why is that so? Because when you integrate the delta function, you are going to get the unit step function. So this one is basically fundamental theorem of calculus. Okay, integrate delta, get unit. So therefore, differentiate unit must get back delta. Okay, so of course we can draw the graph and understand that, but that's we have discussed that before already. Okay, so differentiate unit step, get delta. So we can define W prime as well. So then what we do, just substitute the delta functions and the unit step function back into the ODE. Okay, and then this is our initial condition. So initial condition, we just let it be 0. So 0 initial displacement and 0 initial velocity. So that's considering that the car, right, is moving along the road that is smooth. Okay, until hit the curb at t equals to a. Can any questions with the derivation of the IVP? So this is your initial value problem. So now we are going to solve this ODE using Laplace transform, right? Because there contains delta function and unit step function. Can you use the Duhamels or not? Can use. Okay, but it's just that Duhamels, right? When you deal with discontinuous or non-smooth functions, Duhamels, you might have to perform the integration separately. So therefore, it takes more time. Okay, so unless the question state using Duhamels, whenever you see discontinuous excitation terms, right, it is recommended to use Laplace transform. So here we're going to use Laplace transform to solve the problem now. Okay, so let's solve it together. Okay, first of all, right, it says here that the suspension system is actually critically damped. Okay, well, that's a little bit harsh, but it's fine. Let's assume that it's critically damped. And now you have your mass K and C given. Okay, I mean, you can check lah, right? Basically, C square equals to 4mk. Okay, we can almost just immediately recognize the thing from here. So you can see that critically damped will be C square minus 4mk. That is equivalent to 0. Okay, so you can see the values here conform to this equation. So we just substitute everything in. So therefore, substituting, we're going to get 100 y prime prime plus 400 y prime plus 400 again y, then equals to so the height is 10 cm, but I'll just leave it as h first. Later on, then we can substitute 10 cm inside, because this is in SI unit, and then your 10 cm, you get a decimal that's not very nice to work with. So therefore, we just have C equivalent to 400 times, let me see. Okay, so we factorize out the h. So I think h we factorize out, and then we are going to have C, which is once again 400 times the delta function, t minus a, then plus k, also 400. So the h factorized out already, then times the unit step, t minus a. Okay, so you notice that everything got hundreds inside. So just to make the thing easier, we just divide by 100 throughout. So therefore, we have our ODE, which is y prime prime plus 4y prime plus 4y. And this guy will be, so the 4 can factorize out. So it becomes 4h then. Okay, because there's a 400 here and a 400 here. So therefore, we have a delta function plus a unit step function. Is that right? Okay, so this will be our ODE, right, in this simplest form probably. Okay, cannot simplify further already. Okay, so now we are going to take Laplace transform then, right? So this is our ODE. So now we solve by taking Laplace transform. So we have s squared big Y, and there's no need to handle the initial conditions because they are 0, right? I mean, you sub 0 inside, right? You're not going to have any remaining terms, right? When you take Laplace transform of the derivatives. So plus 4s big Y plus 4 big Y equals to, so 4h is a constant. Okay, then if you take delta function, let's go back to our table. So where's delta function? Delta function is here. Okay, so we want to look at the delta function and the unit step function Laplace transform. Right there. So hence we are having e to the minus as. Okay, so delta function e to the minus as, I can see from here. Then the unit step function will be e to the minus as over s. And that's it. This is our Laplace transform equation. Any objections? Okay, looking good? Yeah. So then you see this part, right? You can factorize. So it becomes s squared plus 4s plus 4, then equals to this side, no change. Then obviously you should try to factorize this second order quadratic equation. Okay, so it looks like this is going to be what? Critically damped. So s plus 2 square. Okay, so then you look at this guy. So later on, you're going to divide throughout by s plus 2 square, right, to get your y of s. And there is a 1 over s plus 2 square here. There's another 1 over s plus 2 square. Okay, what I'm trying to say is this. Because this is the critical juncture where you have to do your fraction manipulation in order to get your inverse transform. Okay, so the 4h take out. Now you see that there's a minus e to the minus as on both terms. So don't leave it inside. Factorize it out so that it's easier to handle. Okay. Then the first term is going to be 1 over s plus 2 whole thing square. Then the second term is 1 over s plus 2 whole thing square. Can right? Can So divide throughout by s plus 2 square. Okay, I get this thing. Then you have to ask yourself at this juncture, right? Do you want to combine the fractions? Okay, this guy, there's no need to combine what? This one s plus 2 whole thing square is like 1 over s square what? With a shift. So no need to combine lah. This one can inverse transform directly. Okay, then what about the other one? The other one need partial fractions. Agree, right? This one need partial fractions to break it up. Okay, so therefore, it's up to you, right? Whether you want to combine or you don't want to combine. Okay, but I would prefer not to combine because this is like very simple already. Okay, so basically this one straight away do partial fractions. Can so I'm going to like just do it here. So by partial fractions, right, this is going to be something over s plus something over, so repeated, so something over s plus 2, then plus something over s plus 2 square. Okay, so you might notice that this term later on will combine with this term. Okay, but it's just that we keep the numerator simple by not combining, right? Yeah, so therefore, if you do your cover up, you're going to get, so this guy is going to be s to be 0. So obviously that's going to be 1/4. Can I cover up s, cover up this guy. Then s got to be 0. So 1 over 2 square. So that's 1/4. Then 1 over s plus 2. This guy cannot. So this guy, let's let it be b. Then this s plus 2 square, right? So therefore you cover up s plus 2 square. Then after that, your s got to be minus 2. So that's minus half. Any objections? So then you want to get your b. Okay, so to get your b, you just substitute any value into the fractions here and solve for b. Okay, any value that is not 0 and that's not minus 2 lah, obviously. Okay, so therefore maybe I just substitute minus 1. So to get b, so if you sub s equals to minus 1, you're going to get 1 over minus 1 times minus 1 or 1 square. So that's 1. So that's equivalent to, so over here, right, it's going to be minus 1/4 plus b over 1 plus minus half. So this is a minus, okay, so it will be minus half. Can Okay. So basically you can solve for b already. So b is going to be, so this will be a minus 1 plus 1/4 plus half. Okay. So you can see that this is going to be 3/4. So this is going to be minus 1/4 then. So we found b. So therefore the whole expression is defined. Okay. So 4h e to the minus as, then you are going to get the first term plus this, right? So it's 1 minus 1/4. Wait, sorry, 1 minus half. Okay, 1 minus half. So therefore you are having half. So 1 over 2, 1 over s plus 2 square. That's your first term. Then plus, then you have your 1/4 times 1 over s. Okay, this term. Then plus this term. So you'll be a minus 1/4 times 1 over s plus 2. So this will be your y of s fully defined. Any objections? Can Okay, no objections. Then you notice that there's a 4 here. A very nice 4 there. So therefore, I'll just multiply in. Okay, so 4 multiply in. So the 1/4 gets struck off. And this guy becomes a 2. Okay, so then after that, ready for inverse transform. So now we solve for our displacement function of the mass of the chassis. So it'll be h. H is a constant. Okay, just leave it out. So now you see, this e to the minus as is going to give you the unit step, right? Because you got function of s times the exponential function in s. So basically, we are looking at this thing here, this guy. This guy. So you see that the e to the minus as, this e to the minus as is going to give you your unit step t minus a. So we just plug in first. So it'll be u t minus a. So now we have to write down the g of t minus a. So you can see that the big G of s is 2 over s plus 2 square. Correct? But it's like, this one is like 2 times 1 over s square. So I just put a 2 lah. Okay. Then 1 over s square is t what? But It's not t, it's t minus a. Because this has to be g of t minus a, what? Not g of t. So therefore, this has to be what? This has to be t minus a, but there's a shift there. E to the minus 2t minus a. Any objections? For the very first term, this guy. The 2 just put one side. Then 1 over s square, right? 1 over s square. This one look like 1 over s square. Right not? So 1 over s square is a inverse transform, give you t. Okay, by right is t e to the minus 2t because there's a shift. But you cannot write down g of t. You want g of t minus a. Can? So therefore, that will be the inverse transform. Then after you have another 2 terms. So just do the same thing. So 1 over s, obviously, is just 1. Then plus. So this is just 1. Okay? Then after you have a minus 1 over s plus 2. So therefore, minus of e to the minus 2 t minus a. So this will be your solution for the suspension system. Any questions using Laplace transform? Okay, good. So we will certainly look at the response given by this function, because actually the wheel displacement is a very simple function. Yeah, you can add it in. There, the height. Okay, so I just put h equals to 0.1 because 10 cm is 100 mm. Then that's 0.1 meters. Then A is trivial. A is just the time where the chassis or when the wheel hits the curb. Okay, so this one doesn't matter. Okay, if I increase, then it will just move to the right. Right, so it doesn't matter. So I'll just leave it at maybe 1. Okay, so what you see here is actually this is the wheel displacement. Right, so if you do not see the chassis displacement, this is the wheel displacement. Okay, so we mentioned that it hits a curb, mount curb. Right, let's say at t equals to 1, at time t equals to 1, and then the curb height is 10 cm. So therefore you can see that it's going to be at 0 displacement, then the wheel traveling nicely along the smooth road, then suddenly mount curb go up. Okay, suddenly jump up. So the wheel is going to jump up, okay, due to the unit step function here. And then what happens to the chassis? It looks like that. Okay, the chassis obviously does not mount curb like the wheel immediately. There is a delay in the response. Okay, there is a delay in the response. That's the purpose of the suspension system, right? So if you were to plot the car chassis displacement in, right, you can see this is exactly the function that we managed to get. You are going to see this. Okay, so once the wheel hits the curb, the chassis wants to go up, but it doesn't go up immediately, right? It goes up in a more gradual manner. You see? Right? It takes longer, right, for the chassis to bounce up. Then after that, overshoot a bit. And this makes sense, what? Right? Because as your mass is moving up, there is inertia of the mass. So the mass will want to go up due to the inertia above the wheel's displacement. Make sense, huh? That's why when you mount curb, right, you immediately feel yourself being bounced up. Then after that, you overshoot. Then after that, you're going to come back. Correct or not? That you feel a bounce. So therefore, this is the bounce. Okay? Then after that, it will go back to the equilibrium state smoothly. So of course, at the end of the day, right, after long enough t, you see that the displacement of the chassis matches the displacement of the wheel exactly. Okay, which is actually the height of the curb because you mount curb already, so the whole thing got to move up by the same amount of the curb's height. Make sense? Can Okay, so this is for critically damped suspension, which is actually harsher than most vehicular suspension systems. Okay, so in reality, most vehicular suspensions, they are underdamped, as I've mentioned before. Okay, or slightly underdamped. So therefore, what you are going to get realistically, and as well as you will have experienced that before, when the fella mount curb, right, the fella is going to overshoot, then come back, overshoot down again, then after it's going to wave, it's going to oscillate a few times before it goes back to the equilibrium position. Okay, so you feel the bounce like up, down a bit. Okay, before you go back to a steady motion. Questions? So this is exactly what we feel. Okay, in agreement with our experience. When you mount the curb or when you chong past the hump at a high speed. Any questions? Can Okay, good. So this will be the last example. Hopefully you are familiarized with the solution approach. So end of topic 7. Okay, I just want to share with you this actual incident of the collapse of this Tacoma Narrows Bridge in United States. Have you seen this guy before? Huh? Tacoma Narrows Bridge? No? Okay, I'm going to show you the video first. Because the fella collapsed, I think, within some weeks of opening.
Footage that right before failure, the bridge isn't oscillating vertically, but in a twisting or torsional motion. The reason for this change in oscillation is still debated, but one of the best suggestions has to do with the aerodynamics of the bridge. Rather than a truss through
Okay,
which
wait,
wind
let
can
me,
flow,
okay, I didn't show you the collapse, so let me show you the collapse.
This flutter eventually created too much stress in the suspension cables, and the bridge failed.
Okay, frankly speaking, initially when I saw the footage of the bridge, I thought this is a ride in Disneyland or something.
The reason for this change in oscillation is still debated.
So you can see the oscillating amplitude of the bridge is ridiculous. Okay, personally, I feel it's ridiculous. It shouldn't oscillate that much if you have built the bridge correctly. Okay, so I leave the link of the story of this collapse here. Right? If you guys are interested, you can watch the YouTube video. Okay, but just to summarize, why is it that this bridge collapsed under very light wind loads? The wind blowing across the wind. Blowing across the bridge. Okay, and the wind is actually not strong. It's just a very light wind. So why is it that the bridge collapsed? One of the reason is that as the wind is blowing through the bridge, it creates this thing called aeroelastic flutter. Okay, so what this guy is saying is that, right, because you must imagine, so now let's say the bridge is like that. So as wind is blowing across the bridge, right, then you can expect, because the bridge is not going to so-called stay perfectly horizontal, right? So it's going to maybe have a certain slight angle, okay, slight twist angle lah. So then as the wind blows, the angle is going to increase. Then as the angle increase, right, due to the stiffness of the bridge, right, it will extend to a maximum angular displacement. Then after that, the so-called stiffness in the bridge is going to force it to come back. So then you come back. But then when it comes back, right, then the wind is still blowing. So therefore, there is the external excitation force. That is the wind force lah. So therefore, there is this swaying back. But when it sways back, the wind force, right, is capturing the wind such that it's going to go back again. So the fellow do this. Okay? So then this aeroelastic flutter frequency matches the natural frequency of the bridge. So then that's what we call resonance. So when there's resonance, the amplitude of vibration is huge. So therefore, too big, right, for the structure to handle. So therefore, collapse. Yeah. No. It may not be worse, in the sense that, right, because the excitation force is causing the torsional aeroelastic flutter. Yeah. So the aeroelastic flutter happens to all structures, in fact. Okay. So it's just that in this case for the bridge, right, it causes a torsional displacement. The torsional displacement is more than the vertical or horizontal displacements. Okay, due to the structure. That depends on whether you want to have oscillations or not. If you are sitting on a swing, you want oscillations. But then if you want to have a stable structure, you don't want oscillations. Can Okay. So therefore, basically what happens is that one of the big reasons behind the collapse, right, due to the wind, the slight wind, is because the engineers didn't calculate or they didn't simulate the frequency response of this structure. Okay, so that means the eigenvalues, they didn't model carefully. Okay, because it's the eigenvalues where the frequency of the vibration manifests itself. Remember the alpha plus I beta, right? your I beta, that beta term, is the natural frequency. Where's the beta term? Okay, this guy. Can you see? Alpha plus minus I beta. The beta is in the frequency of vibration. There, this is the displacement function. Okay, so beta is representing the angular frequency, which relates to the natural frequency of the structure. Okay, yeah, so we are done with topic 7. We shall take a break before we move on to the tutorial. Okay, so let's take a break. Maybe let's have a break till 10:20. Okay, so for our tutorial 7, for the first question is about derivation of the general solution for the second order ODE in case that your eigenvalues are real and repeated. So this one we didn't go through in the lecture, right? Because I want you to try deriving this guy. So I'm not sure if you guys managed to get it. Do you manage to get the blue box solution for the homogeneous second order ODE? Can get? Got it? Cannot get? Okay, so let me just quickly go through. Okay. So this is about trying to decompose the ODE into a system of first order. Because if you look at the approach, right, this is very standard. This is the approach. So let me just continue from here. So you can see that the general form of our second order ODE, ay prime prime plus by prime plus cy equals to 0, right? And then we're supposed to show that this is the general solution. Okay, so where we start is from the conversion of the second order ODE into the first order form. Okay, so basically this part, right, is by letting v to be y prime. So this one we discussed before, right? So if you let v equals to y prime such that v prime equals to y prime prime. So you can see that y prime prime becomes v prime, right? Then y prime here is v. Then the cy, you just let it be. Okay? So which means that this is a first order ODE involving v and y. Can? So you can see that your first ODE, right, is v equals to y prime. So therefore you get y prime equals to 0 times y plus 1 times v. Let me change the color. This guy. This is what you introduce. So this is the first equation. Okay? V equals to y prime or y prime equals to v is the same thing, right? Then this is the second equation. This guy is the second equation here. So your v prime after you isolate, right, must be minus c over ay, minus c over a times y. Okay, then minus b over a times v. So you can see from here, isolate the v. Isolate the v prime. So it will be minus c over a times y minus b over a times v. And you can write it in this matrix form. Can? Okay? Yeah. So at this juncture, because your eigenvalues is going to be what? Is going to be real and repeated. Right? So this is your matrix A. This guy is your matrix A. Okay? So when you try to solve this guy, right, you are going to have real and repeated eigenvalues. So determinant. So determinant of A minus lambda I equals to 0 is going to give you, so from here, you get lambda square minus b over A. So it's a plus b over A lambda plus. So the determinant, right, is going to be minus c over A. Minus, wait, is it minus? Oh, sorry, it's a plus. plus C over A. So this guy equivalent to 0. So let's say your A, B, and C values, you are going to get repeated eigenvalues. Okay, so lambda equals to lambda 1, 2. So this is repeated. So let's write it as real and repeated. Oh, that means the A, B, and C coefficient values turn out to be such that this is a perfect square. So this is like something like lambda minus lambda 1 square equals to 0. So you have repeated eigenvalue lambda 1, for example. Okay, so because it depends on the A, B, and C values, right? What kind of roots you get. Can Yep. So therefore, if you get real and repeated eigenvalues, right, then you notice that from the lecture, so this one no need to resolve, you notice that for your eigenvalues, you're just going to get the eigenvector being 1 lambda n. Okay? 1 lambda n. I mean, you can sub in any general eigenvalue, lambda, right? And then you solve it, and you get 1 lambda n as your eigenvector. So which means to say that from here, your eigenvector, so only one eigenvector, because real and repeated, so only one eigenvector, V1, which is 1 lambda. Okay, because your lambda 1 and lambda 2 is the same one, so it's just lambda. So I just put it as 1 lambda lah. Okay, because this guy is real and repeated, so only one eigenvector, which is just 1 lambda. Can Then obviously you need the other eigenvector. Okay, so what would be the other eigenvector? Hold on. So what would be the other eigenvector? You have to solve the same equation again, right? For the generalized eigenvector. So therefore, need generalized eigenvector V2. Okay? So basically we solve A minus lambda I times V2 equals to V1. But what is this equation? This equation you can just obtain from here. So it'll be minus lambda 1 minus C over A minus B over A times V2, which is just XY, then equals to 1 lambda. Okay, so put your V1 on the right side because this is your generalized eigenvector equation. Okay, so therefore, if you were to solve it from the first row, first row easy. So I mean easier. So just solve from the first row. So we're going to get minus lambda x plus y equals to 1. So it goes to show that y equals to 1 plus lambda x. So therefore, in this case, you can choose your x to be 0. So V2, the generalized eigenvector, will be 0, 1. So just choose x to be 0, and your y can be 1. Any objections? Of course, you can choose like 1, 2 also lah. I mean, sorry, 1 and 1 plus lambda, but that's more difficult one. Okay, so just choose x to be 0, and your y automatically will be 1. Can Yes. Yeah. Oh, apologies. I noticed that I made a mistake. This one minus lambda, I forgot to minus lambda here. Hold on. There should be a minus lambda because you need to minus lambda on the diagonals. Yeah, JVL, what's your question? 2 what? 2 minus eigenvalue. This minus eigenvalue, this minus eigenvalue? Correct. Oh, okay. I see. Okay, thanks for your question. So you can see that I need to minus lambda here as well. Okay, but then the equation here no change. So therefore my V2 is 0, 1, right? So which means that I can write down the general solution for this matrix equation already. Okay, so from here, right? So from here, I'm going to have y of t, v of t. My solution is going to be what? T times e to the jt. Correct? J, because this one generalized. So e to the jt times c. So this is my general solution. General solution is. Okay, in case you're wondering where this is coming from, right? Topic 6, Topic 6. Topic 6. Right. Right here. Okay? Our matrix is defective. Can? Matrix A is defective. So you have to use Jordan decomposition. P times E to the JT. By right, is P inverse times X naught. Right? But because you're solving for a general solution, what? So therefore, just let it be C. P times E to the JT times C. Yes. Sorry? Use the formula from chapter 7. The thing is, I'm trying to prove the formula from chapter 7. That's what the question is asking for. Okay? Yeah. So therefore, this is from topic 6. Okay? Yeah, but then your P, okay, what? Your P already found already. So it'll be 1 lambda and 0, 1 times e to the jt must be e to the lambda t, e to the lambda t. Then on the top right must be te lambda t. Then this guy is a 0. But C, just C1, C2. Okay? So then therefore, if you multiply out this guy, you will get the general solution. So you can see that this guy is going to be, let me multiply out the last two matrix first. So this is C1e lambda t plus C2te lambda t. Then the bottom is just C2e lambda t. So therefore, if you multiply out again, then you're going to get, so this is a 1, 0. So which means that it's only the first row. Okay? Then the second row is just going to be lambda times the first row plus the second row. But that's not what we are interested in. So you notice that the first row is already your answer. Okay? So what we want is the y of t. So the y of t has to be the first row. So therefore, y of t is e to the lambda t C1 plus C2t shown. Any questions? No, it's stated in the question. Because the question says, right, for the second order homogeneous linear ODE, you have to show that the general solution for real and repeated eigenvalues, right, is this guy. So therefore, we have to consider where your lambda is real and repeated. Okay, which means that from the eigenvalue equation here, right, you have A, B, C so-called nicely chosen such that you only have one eigenvalue. So therefore, you have only one eigenvector, one lambda. So when you solve for the generalized V2, right, you notice that your V2 is 0, 1. Then you plug inside the general solution form for topic 6. Then you're going to get the general solution for the second order ODE here. Yeah, correct lah. Yeah, because eigenvalues can be 3 types ma. One is real and distinct, then you just use this one ma, already derived for you already. Then the second one is, if it's complex, then you just use this guy lor. So already derived for you here. Then the third one I never derived there. So I'm supposed to derive in tutorial 7, which is in the question 1. So which is what we have done here lah. Any other questions? Okay. Yeah, so that's for question 1. So for question 2, homogeneous. Basically, this kind of question is a giveaway lah. Right? Just solve for the eigenvalue, see which type it is, then after use the correct blue box. This one do I need to do? Very good. No need, this one? Okay. So for the third question is the extension to get the Duhamel's principle, which is actually just working on YP here. This one do I need to do? Okay. So it's a continuation from where we left off from question 1, because we just extend from here can already. Okay, so we are going to make use of the concept of the Duhamel's principle, because this is the so this is the general solution for the homogeneous problem. Okay, this one homogeneous problem, right? So what is the homogenized problem? This one, can see the f of t here, right? So how do you solve for the particular integral? Is you have to extend from the homogeneous problem. Okay? So the story is like that. So from here, you write down the homogenized IVP. Homogenized initial value problem is, so the homogenized IVP means, right, make this homogeneous. So just remove the f of t lah. So my prime prime plus cy prime plus ky equals to 0. But the f of t, you plug into the initial condition. Okay? And then, because we know that when we plug into the initial condition, we must plug into the initial velocity. So this y naught equals to 0. And y prime naught must be f of tau over m d tau. This one I just copy from here. Wait, so we apply the same thing here. There. Can see? So the homogeneous IVP is equals to 0. Then y of tau equals to 0. Y prime tau equals to f tau over m d tau. Okay? Because the f of tau over m is an acceleration. Because force divided by mass is acceleration. Then acceleration times time is just velocity. Okay? So therefore, going back to my problem here, which I made a mistake. This one should be at tau, not at 0. So the initial condition is taken at tau. Okay? So once you have this, right? Now, because what is the solution? The solution is this guy, right? Correct or not? So from here, because it's homogeneous, so solution, or let me write, homogeneous solution is this guy. So you just copy and paste. Okay? But then if it's this guy, then actually what you need to do? We just find the C1 and C2 what? Correct or not? Then you never apply the initial conditions yet, so therefore now apply lah. So y of tau, apply initial condition. Apply initial conditions. So y at tau equals to e to the lambda tau. Then C1 plus C2 tau equals to 0. But then e to the lambda tau cannot be 0. So that means that you must have C1 plus C2 tau equals to 0. C1 plus C2 tau equals to 0. Okay, since e to the lambda tau is not going to be 0. It will approach 0 lah. Okay, but it can never be 0. Okay, so that's the first initial condition being applied. Then the second initial condition being applied, right? You need your y prime. Okay, so from here you cannot simplify. So which means that you got to differentiate. So let's get my y prime of t first. So y prime of t, as you can see from here. So lambda e lambda t, you have to use your product rule. So lambda e lambda t times c1 plus c2t, then plus e to the lambda t, then times c2. Can use product rule. Then after that, you just simplify. Maybe e to the lambda t. Then after that, I have c1 plus c2 lambda times c1 plus c2. Wait. Sorry, lambda c1 plus c2. Lambda c1 plus c2. Then plus a c2t. Okay? So now apply. So y prime at tau equals to e to the lambda tau. Then after you have this bracket, which is lambda c1 plus c2 plus c2 tau. Yeah, you're right. My bad. I missed out a lambda here. Because this one got c2t lambda. Thanks. Okay, I should have a lambda here. That means this guy got lambda. Can Yeah, so then this guy must be equivalent to f tau over m d tau. F tau over m d tau. Agree, Okay. Yeah, so you see this one, C1 plus C2 tau. C1 plus C2 tau. Wait. Nice. There's a C1 plus C2 tau here. Okay, and it has to be 0. Okay, so let me rewrite this. Okay, this guy, right, is this part is lambda. Then C1 plus C2 tau plus C2 Correct or not? This one. But C1 plus C2 tau is 0 Okay? So I underline C1 plus C2 tau is 0. So that means this guy is 0. So therefore, that simplifies a lot. So you're only left with C2 times e to the lambda tau. So C2 e to the lambda tau equals to the right-hand side. So therefore, you know what's your C2 already. So which means C2 is just e to the minus lambda tau, reciprocal, times this f of tau over m d tau. So you found C2. But if you found C2, then C1 can also find already. Because C1 is just minus C2 tau. So C1 equals to, okay? So from here, C1 is minus C2 tau. So you just put a minus, then times tau. So which is this whole thing times minus tau. Is that okay? So then putting it all together, your homogeneous or homogenized solution for one instance of the excitation. So let's call it y tau at t is gonna be. So the original solution looks like that. Hold on, let me copy. Okay. But then your C1 and C2 can just plug in because C1, C2 solved already. So it will be e to the lambda t, but your C1 and C2 both got this e to the minus lambda tau term. So put a big bracket. Then this guy plug in. Then your C1, right, is just there's a minus tau. Then plus C2t plus C2 is just this one, right? So it's just t. Okay? Following? It comes from this guy. So I underline. Like this one is C1. C1, right, is this guy. So then your C1 here, ma. So C1 is this times this, ma. Correct. Then your C2, because it's C2t, ma. So that was C2t, just this thing times t, okay? Can see, right? Yeah, so just write it a little bit neater. So writing it neater, right, the exponential term can combine. So become e to the minus lambda times t minus tau. Is that correct? Oh, sorry, lambda times t minus tau. So e to the lambda times t minus tau. Then after that, you have a t minus tau. This term is t minus tau. Then after that, you have your f of tau over m d tau. Okay? This is just for one instance. So therefore, the particular integral, so yp of t. So particular integral, you must integrate this from t0 to t. Okay? Did I put 0 as t0? Okay, so t0 is 0. So integrate from 0 to t, this whole thing. So then that's your particular integral. Okay? So therefore, the Duhamel's principle y of t must be yh of t plus yp of t. So it has to be this guy plus this guy. Is that right? 1 over m can take out lah, because m is a constant. 1 over m you want can take out. It's fine. Okay, so let's mark attendance.